Hello, Physics 2. Welcome back. This is part 2 of the chapter 36 slides. In the first part, we learned some of the history of magnetism and some of the basics. And in this part, we're going to go a little bit further with that. So let's get started. As soon as this loads, we'll get started. So who was it that discovered that a current moving through a wire created a magnetic field? It was a Danish physicist named Hans Christian Ørsted. This guy. Pleasant-looking fellow. Nice neckwear. So who discovered that a changing magnetic field near a loop of wire caused a current? Our old friend, Michael Faraday. So here's the old Michael Faraday. There's also younger pictures of him. So those two ideas are kind of flips of the same thing. Moving charge causes a magnetic field, and changing magnetic field causes charge to move. It causes a current in a wire. And who was it that put these ideas and many others together and discovered that light is actually electromagnetism and is really one of the giants of physics? That would be Scottish physicist James Clerk Maxwell, that guy there. So we learned a right-hand rule last time. How did that right-hand rule go? That was Ampere's right-hand grip rule, or just the grip rule, which says that if you were to grab a wire, just with your fist, with your thumb up, such that your thumb was pointing in the direction of the positive current, also called the conventional current, then the magnetic field created by that current would wrap around the wire in the same direction that your fingers wrap around your fist. So, question 5, oldie but a goodie. What is Newton's third law? This is for every action, there's an equal and opposite reaction. So if one object exerts a force on a second object, well, that means the second object must exert an equal and opposite force back on the first object. So the force must be just as strong, and it must be in the exact opposite direction. So keep that in mind. So what Ørsted discovered, moving charge. So you've got a current near a compass, it's going to deflect the compass needle. So we would say that the current carrying wire exerts a force on the compass needle through the interaction of their magnetic fields. So they're not actually touching, it is force at a distance. It's through their interaction of the magnetic fields. So current carrying wire exerts force on compass needle. What would Newton's third law say about this? Well, it would say the compass needle must exert an equal and opposite force back on the current carrying wire. So magnetic fields exert forces on moving charges. So again, I mentioned this last time, stationary charges do not create magnetic fields, only moving charges do. And stationary charges do not feel a force from magnetic fields. Only moving charges do, and only sometimes. We'll get to that. So moving charges has in when you have a current moving through a wire. That is moving charge. So if you have a proton or electron just sitting there on the table and there happens to be a magnet nearby, they're not going to interact. But if you were to move either the proton or you were to move the magnet, which would cause the magnetic field near the proton to change, that would create a force. So I made this picture myself in Google Drawings. It took a while, but I'm pretty proud of it. So you've got a current flowing through a wire as shown between the ends of two bar magnets. So your current's going like this, and we've got to think in 3 dimensions here. So yeah, X is out towards us like this, Y is left and right, and Z is up and down. So if our magnets are arranged like this, which way will the magnetic field point? We would say it points this way. It points to the right. It goes from the north to the south. And then again, remember, it actually loops around. All magnetic field lines actually form closed loops, but in the area we're interested in, we're going to say the magnetic field just goes left to right like this, and we don't care what happens outside of that area. So we're getting a second right-hand rule here. If you've got that current going that way, into the page, and you've got your magnetic field going to the right, you're going to get a force going down. So you've got to do another another right-hand rule. So point your thumb into the page. So do this now as you're actually watching this video. Point your thumb into the page, as in like towards your screen. Hold your fingers out to the right. So your thumb is the direction of the positive current. The direction your fingers are pointing in is the direction of the magnetic field. And notice, if you're doing this with your right hand, your palm is facing down. So that's the direction of the force. So this is another right-hand rule. We can call this the second right-hand rule, or you can call it the cross product right-hand rule. So you can look at it again this way. If you hold your right hand in front of your face so that your palm is facing you and your fingers are pointing up and your thumb is pointing to the right, your thumb is the direction in which positive charge moves. People have different ways of stating these rules, and some of them I think are terrible. I will always try to make your thumb the direction of the current or the direction in which positive charge moves. Your fingers are the direction in which the magnetic field goes. So we're not talking about the magnetic field that is created by this current. We're talking about this current happens to be moving through a magnetic field that was already there. So yeah, your thumb's pointing to the right, the magnetic field, that's the current pointing to the right. Your fingers are pointing up, that is the magnetic field pointing up, and your palm is facing towards you, and that is the direction of the force on the positive charge. So you can't see it, but right now I'm sitting here with my palm facing my face like this. It looks kind of silly. You'll do that a lot in this chapter. But anyhow, you push with your palm. So I always use the palm to represent the direction of the force. If you were going to push on something, you wouldn't jab it with your thumb point. You wouldn't jab it with the tips of your fingers. You would push it with your palm. So your palm represents the force. So if we look at this magnetic field here, which way is this magnetic field pointing? Are we looking at the tail feathers of the arrow, or are we looking at the tips of the arrow? We're looking at the tips of the arrow. That means this magnetic field must be pointing out of the page towards us. So through this magnetic field, there's going to be a wire, and through this wire, there is a current going down. So arrange your right hand so that the magnetic field, the tips of your fingers are pointing towards you, and your thumb is pointing down. So I purposely made this kind of an awkward one. You should have your elbow out in front of your face. Your fingertips probably right about at your nose and your thumb pointing down. So which way is the force felt by the wire? Well, which way is your palm going? Your palm is going to the left. So that's the direction of the force. So we have a formula now. We love formulas. So the formula for the force on a current carrying wire in a magnetic field, and we've got it two ways here. The top way is the vector way. There's a full, very rigorous way of doing vector math where the force is equal to I, the current, times L, the length of the wire going through this magnetic field, cross product with B, the magnetic field itself. So that's the vector version if you're interested in the higher maths. In college, you'll have to do it this way. We're mostly going to do it this way. This is our version. This is kind of the scalar version. We're just going to say F equals ILB sine of theta, where theta is the angle from L, the length of the wire, to B. So this formula works when you have straight wires and constant magnetic fields. So yeah, I is the current, in amperes, of course. L is the length of the wire. That'll be in meters. B is the magnetic field in units of Teslas. And theta is the angle from L to B. So you need to know that angle as well. So here's Nikola Tesla. So quantity, symbol, unit, and vectorness. Your quantity is magnetic field. Its symbol is B, which should have a hat on it, but again, can't do that in Google Slides. The unit is the Tesla, which if you write out the unit, you use lowercase t. If you just want to use the shorthand version, you write a capital T for Tesla. And is this a scalar or a vector? Magnetic fields are definitely vectors. They do wear hats, even though sometimes we get lazy and leave them off. So you have a 12.5 centimeter wire carrying a 3.75 ampere current going through a uniform magnetic field of 0.825 Teslas, and it's going as shown. So in what direction is the force? Well, point your thumb up because that's the direction of the current. Turn your hand so that your fingers are in the direction of the magnetic field B, and you should have your palm facing the screen because this force is going to be into the page. So the thumb is the current, your fingers are the magnetic field, and the palm, the way your palm is facing, that's the direction of the force. And again, this is our second right-hand rule. This is not the magnetic field created by this current. This is a magnetic field that is there, and this current is going through it. So what is the magnitude of the force? Well, just take this formula right here, plug in the things. Be careful because it's not 12.5 meters, it's 12.5 centimeters, which is 0.125 meters. Plug that in, times the sine of 90, because the angle between this, between the length of your wire and the magnetic field is 90. And you get F is equal to 0.387 newtons. So that angle, is it 90? Not really. So yeah, I'm being kind of sloppy, but this is how we do these problems. So technically, you're always supposed to measure, if you're doing this the rigorous vector math cross product way, you always measure your angle from the length of your wire through which the current is going to the magnetic field. So I really should measure from here down to here. So I shouldn't call that 90, I should call that negative 90. And it matters because sine of 90 is 1, sine of negative 90 is minus 1. So when I do this math, I should really get this answer here. However, we're going to handle that a different way. The negative sign in that answer really means that your force is going into the page. So if you do your vector math rigorously, it will give you a positive or negative sign, and that will tell you the direction. But we're just always going to use the right-hand rules to figure out the direction. So yeah, if you look at the XYZ axes here, we got a force negative, meaning in this case it's going into the page. Sometimes negative will mean left, sometimes negative will mean down, but in this case, our right-hand rule told us it was going into the page. So let's just always use the positive values. I mean, pay attention to the directions of things, but use the positive values and use the right-hand rules to figure out the directions of things. Right. So if we're looking at this, what are we calling the angle here? Is that 30 degrees or is that 60 degrees? We're going to call it 60 degrees. Oh, that X is in the wrong place. Sorry, I've been changing my slides around. That X should be Xing out this right here. We would call this 60 degrees. Really, we should call it negative 60 degrees because we're supposed to measure from this length to the magnetic field. So we should be going that way. But yeah, call it 60 degrees. See, that's where the X is supposed to go. So what is the direction of the force? So your thumb is the direction of the current. So up and to the right. Your magnetic field is going to the right. The direction of the force is still going to be into the page. So yeah, our thumb is not going directly up, but there is some component of our thumb, that is going up. So you're still going to get a force into the page. So what is the magnitude of the force going to be? Well, you just do the math. So same current, same length, same magnetic field, but this time instead of sine of 90, we have sine of 60, and we get a slightly smaller number. We get 0.335 newtons going into the page. So in this case, now we've got our length of wire going directly to the right, and the current is going directly to the right, and the magnetic field is going directly to the right. So what is the direction of this force, and what is the magnitude of this force? Trick question. There is no force. The right-hand rule, your thumb has to be at right angles to your fingers if you're doing this second one, the cross product rule. If the current is going in the exact same direction or in the exact opposite direction, has the magnetic field, you're either going to have sine of 90 or sine of 180. In either case, the answer is 0. So in this situation, there won't be a force on this wire because of the current and the magnetic field. So what are the symbol, unit, and vectorness of magnetic field? Well, the symbol for magnetic field is B. The unit is Tesla. And is it a vector or a scalar? It is totally a vector. So here are the two formulas we've learned so far. The vector version over here, the scalar version over here. We'll mostly use this one. You can use this one if you want to do vector maths. So what was the first right-hand rule that we learned? So not the one we learned today, the one we learned last time. That was Ampere's right-hand grip rule. So if you've got a current going through a wire, grab the wire such that your thumb is going in the direction of the current, and then the magnetic field caused by that current will wrap around the wire in the same way that your fingers wrap around your fist. You have to use the right hand for this. And what was the second right-hand rule that we learned? The one that we learned today. That should be hyphenated, apparently. I'll go back and fix that. The second one is the cross-product right-hand rule. So if you're crossing, A by B, A will be your thumb, B will be your fingertips, and the direction of the cross product will be in the direction of your palm. So, yeah, in this situation, point your thumb in the direction of the conventional current, point your fingers in the direction of the magnetic field that's already there through which this current is flowing, and the force on this wire will be in the direction of your palm because you push with your palm. And that's it for part 2. So hopefully you found that helpful.